Hi there, and welcome to the first video in a series about fundamentals of electric circuits. The goal of this series is to be something similar to what you would find in a typical to introduction circuits course. But first, a quick disclaimer. Errors may be created somewhere in this video series, but I will try my best to minimize the errors and create the best quality videos that I can. Let's start by talking about charge. In an atom, there is a nucleus which is made up of neutrons and protons. As the name states, protons have a positive charge and neutrons have no charge. Since the nucleus is positively charged, it attracts electrons which form a cloud around the nucleus. Protons and electrons have the same charge but an opposite polarity. Charge is measured in coulombs, which is the amount of charge that is transferred by 1 ampere of current per second. Therefore, current is simply the flow of charge from one place to another. Current can be DC, direct current, which means that the current is always flowing in one direction, or AC, alternating current, which means it will flow in either direction. For 1 coulomb of charge from electrons, you would need 6.24 times 10 to the 18th electrons. So if you have 1 ampere of current, that means that in that 1 second, all those electrons are transferring to another place. In order for current to flow, there must be a force. We call this force the electromotive force, or voltage. Since power is the rate of work done, we can also define P equal to VI. Let's take a look at this example. Imagine the water in these cups as the charge. When I pour the water, the charge is being transferred from one glass to another. This transfer is the current. For this current to happen, I need a force, which is the mass of the water times gravity. We can also demonstrate the conservation of energy with a solar panel example. Let's say I'm trying to figure out how many solar panels and batteries I need in order to go off-grid. The graph on the top left is the power output per solar panel per day in hours, and from this we can find the total energy received by integrating, and we get 1,666.7 watt-hours. Now the unit watt-hours is kind of unique to the electrical field. Basically what it means is that if I have an appliance, let's say a hair blow dryer, which is 1,000 watts, and I run it for 1 hour, that's the amount of energy, 1,000 watt-hours. For the average US home, we usually use around 900 kilowatt-hours per month. Thus, I need 18 solar panels in order to power the house. For storage, we'll use average car batteries, which can store 1,440 watt-hours. Therefore, we need 63 car batteries in order to store enough energy for 3 days. There are 3 different types of materials. Conductors, which have charges that can move freely. This includes metals such as copper and aluminum. Insulators, which do not have any free charge carriers and thus do not conduct. This would include things like plastic, ceramics, and wood. And semiconductors, which are somewhere in between. They can either be conductors or insulators depending on their configuration. Resistance is the measure on how much an object resists or slows down the flow of current. The unit of resistance is ohms, and different materials have different resistivities. Ohm's law relates the resistance with the voltage and current, and thus we can understand the resistor, which is a common circuit element. Electric circuits are made up of different components. For now, let's just deal with sources and resistors. An ideal source can either be a voltage or a current source. They can be independent or dependent. For a voltage source, the polarity of the voltage is dictated by the sign in the circle. Batteries are an example of a voltage source, however they are not ideal. An ideal independent source, like an independent voltage source, means that no matter what happens between terminals A and B, the voltage will always be maintained. The same can be said for a current source. The current will always flow in the direction dictated by the arrow between A and B, no matter what happens at terminals A and B. Dependent sources output a voltage or current depending on a mathematical relationship to something in the circuit. It is common practice to use these to model different types of components in a circuit. Now let's look at how these elements are connected. In circuits, there are 3 things you must keep in mind: nodes, branches, and loops. A branch is a single element, like a resistor or a voltage source. A node is where any one or more of these branches meet. If you look at the drawing in the bottom left, you can see that that circuit has 3 nodes, and all of the branches are connected by ideal wires. A loop is a closed path in a circuit. Thus, if I start at one node, pass through a set of other nodes, I should be able to return to the original node. An independent loop means that it contains at least one branch that was not included in any other independent loop. Now time for the laws. We already saw Ohm's law, but there are two other laws that we use all the time in circuits: Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law states that the sum of the currents entering a node must be equal to 0. In other words, the current entering a node must be the same as the current leaving the node. Kirchhoff's voltage law states that the sum of all of the voltages in a loop are equal to 0. To better understand KVL and KCL, let's look at this example. In this example, I must find voltage VO. I start by labeling all of my nodes, A, B, C, and D. I then choose one of my nodes to be my reference, or 0 volts. In this case, I chose node D as it has the most amount of connections. Now, knowing what we know about ideal voltage sources, and since node D is 0 volts, I automatically know what the voltages are at nodes A and C. The next step is to label all of my currents. From node A to node B, I have I1 flowing, and from B to C, I have I2 flowing. Using KCL, I can write a current relationship for node B. And since we are using resistors, I can use Ohm's law to convert that equation into a voltage relationship. From there, I can solve for the voltage at VB. Now, voltage VB is in reference to node D. Thus, in order to figure out what I0 is, I must subtract node VB from VD. Therefore, VB is equal to VO. This concludes part 1. Since this is an experimental series for me, I would like to know what you guys think in the comments below. More importantly, I would like to know if you want me to continue making this series. Remember to like this video if you did, and thank you for watching.